today I will introduce the RISE, which is robust integral of sine and error control, and cooperate with the multi-layer neural network. This is one major advantage of using RISE control, which can avoid high frequency switching, and that happens before in the sliding mode control. Okay, so RISE control, in other words, is improved version of high frequency control, okay, which is sliding mode control. So the conventional way to design controllers, for example, given these already Lagrange systems, the conventional way to design that is we design filter tracking error for the first step. Then we substitute the dynamics from MQ double dot, right? And R, the filter tracking error is defined as E dot plus alpha E. Take the time derivative, now we can see that the double time integral, okay, E double dot, which give you the control access in MQ double dot, right? In RISE control, because we want to eliminate high frequency switching, so that we take one more time derivative here in the dynamics, and here you will see that the tau, you need to take one more time derivative on tau. We design the controller on tau dot. Okay, but before we design the controller on tau, so that's the difference. For example, given nonlinear system described by this, which is x dot equal to fx time plus ut. U is the control, f is the nonlinear dynamics, and f can be upper bounded by constancies. Let's compare between conventional design and RISE control. Conventionally, you will design the default function, which is a quadratic form here, and you take the time derivative, you substitute the closed loop dynamics here. Then you design a high frequency control, beta sine x. Beta is greater than the absolute value of uncertainties. This is a high frequency control. But for RISE control, we are not design controller on U. We design controller based on U dot. But when implement, we implement U. And in U dot, we put a high frequency term, which is beta sine x in U dot for RISE control, okay, which is this. But in conventional control, we put sine x directly in U. Okay, that's the difference. One is in U dot, one is in U. So when you implement a controller, you need to take the time integral on this U dot. This U is what you really implement in real case. And because you integrate U dot, which means you integrate the sine function. And that's how we eliminate the high frequency switching. Let's say we are doing a regulation control, which we want x goes to 0. So we design R function such that R dot is x double dot equal to alpha x. And we want x goes to 0 as t go to infinity. Then from x double dot, we can substitute the open loop dynamics from x double dot. This is filter tracking error. And okay, so given this open loop dynamics, the conventional way to design the controller, this is the open loop dynamics. Then we design U, okay, design this, which could be U equal to some feedback and some high frequency term. This is high frequency control. For RISE, we will take one more time derivative, okay, compared to here. We take one more time derivative because we want to eliminate the high frequency terms. We move the high frequency terms in U dot. Right here is in U. So similarly, you can design U dot to be again minus KR minus beta sine x. Here is the same. When you implement the control, which is U, you need to integrate this U dot. By definition, this is U. And because this U dot, which means you integrate all these terms, okay? And you will integrate some discontinuous terms, high frequency terms. it becomes continuous. In here, the controller is not continuous because of the sign function. Now it's continuous, right? Because remember, sign function is this. Okay, but when you do the integral, tau, it becomes continuous, right? Here the discontinuity is at 0, right? Here you have discontinuity, but here is always continuous, which means high frequency switching doesn't exist now. So this is the advantages. The downside analysis here has to be redefined or have to be redesigned. All this process, all this stuff, all this analysis has to be we need to redo the whole analysis. That's the reason that we put P term here. Okay, P term. P is a positive definite value function that can be designed. In this slides, the objective is just for you to do a quick comparison between the conventional control and rest control, the advantages and the downsides. So as I say, when you take the one more time derivative compared to the conventional approach, you take one time derivative on u, which is u dot. And of course, you take one time derivative on f, they come out with some nonlinear terms. You divided the dynamics into two groups. One is the terms that can be upper bounded by constant. One is the term that can upper bounded by functions, the error functions. And here is the r and x. So nd can be upper bounded by constants as well as nd dot. And n tilde is the function that can be upper bounded by x and r. Z is a color matrix that include x and r. And here is how you design u dot. You put a high frequency term in u dot. Next, you do the you can obtain the closed loop dynamics here, where you will see the sign function, the high frequency terms. You do the stability analysis, and the requirement for P here is also designed by the users, but the requirement is P has to be 0 at 0, and P is greater than 0 in when it's not 0. In other words, P is a PD function, okay, and it's radially unbounded. So when you take the time and the form, the P is in this form, which is a constant terms minus some L function. L is the functions defined here. Okay, it's R times ND minus beta sine X. In other words, in P, you have integral of sine function. That means that the sine function here is to cancel out with another sine function in the dynamics. Sine function in R, which is in P, right? Because P is the integral of L function. And that sine function is designed to cancel out with another sine function in R dot, which is this. So here you can see that ND will cancel out with another ND coming from the P terms. Beta sine X cancel out with another beta sine X from P. Okay, one is from P, one is from R dot. And finally, you can see that the V dot will be upper bounded by is NSD because P term is missing, okay? Because Z is defined as a combination of X and R. Z is a vector which has elements of X and R. So it's a NSD, V dot is NSD. And you can use invariance theories to show that Z will go to 0 as t goes to infinity. Because rise is the main advantage for rise, it can be considered as a robust control, right? It can cancel out uncertainties because it contains the high frequency terms in the U dot. But in U, it's not high frequency anymore. But this sign function can be used to cancel out some uncertainties because in here, for example, F is the uncertain function, right? It can be upper bounded by constants. We design beta sine X as a robust term to cancel out these uncertainties. And compared to this, that controller is continuous as the advantages, right? So we want to use RISE cooperate with multilayer neural network because we know that the neural network, which can be considered as a black box, and that can be used to approximate a nonlinear unknown functions. You can only do approximate. You cannot truly use neural network to represent the nonlinear functions, right? Because they always exist an approximation error. And RISE can use to cancel out the error, the error which can be upper bounded by constants. You will expect to see that using RISE control and multilayer neural network, you can achieve one, you can control a system with unknown nonlinear functions. Second, you can achieve a syntactic stability, even though that neural network cannot approximate any nonlinear function. So that's the two advantages when you combine RISE control with multilayer neural network. So given the same order Lagrange system we mentioned before, we designed three tracking errors. The first tracking error is the difference between QD and Q, desired trajectory and the current trajectories. And you have two filter tracking errors. We used to have only one, but now because we want to take one more time derivative on the error, okay, so we have to use another filter tracking error, which is 2, filter tracking error 2. And by using this R function in the open loop dynamics, this open loop dynamics can be rewritten as this form. And FD is the function, is this function along the desired trajectories, along the desired QDs, so that the mismatch between F and FD will be included in S. S is this. Okay, it includes all the mismatch between the desired F and the true F. So next, you take one more time derivative on MR that obtains MR dot minus M dot R and plus the other terms. And this is the U. This is the control we design. And the control, okay, this is U dot. Remember here we have tau, right? This is open loop dynamics. We have tau here. And next we take one more time derivative on this equation. So every term will have one more time derivative. So tau becomes tau dot. And tau dot we design, with the control we design as this. You can expect that you can see the high frequency term in here. FD hat dot is the feed-forward term in the controllers, right? We want to use this FD head dot term to track the desired trajectories. And the second term contains the feedback terms and robust term. Robust term is dominate the mismatch terms that can be upper bounded by constants. And another one is for feedback. Same as here. This one is for feedback. This one is for robust. For mu dot, we design mu dot as this, which contains feedback and high frequency terms, which can be considered as robust term. Remember, here we use multilayer neural network to approximate the nonlinear function. This is estimate of the desired nonlinear function, FD hat, and that was approximated by the multilayer neural network. And this W hat and V hat are the weight to be estimated, similar to Y theta hat in adaptive control. The weightings, these are the weighting to be estimated, right? And there's some update low for theta hat. And this is the uncertainties. And they can be upper bounded by constants, which according to property 3. So next, you can regroup in these dynamics, okay, into these equations. And the untilde terms contain the terms that can be upper bounded by states. And n terms are those terms that can upper bounded by constants. And this one can be cancelled out with the adaptive law that used to estimate W hat and V hat. Eventually, when you do the stability analysis, you will see this. You design the ball function, which contains these three terms. They are associated with tracking error. And you had add another two terms to help to cancel out the high frequency terms. But it requires to be positive definite, because in a double function, this function has to be positive definite. So every term, which is P and Q, have to be positive definite. Okay, so when you take a time derivative, you substitute corresponding dynamics and substitute P dot, Q dot, you will get this. So P dot is associated with these terms. Q dot is associated with the W tilde and V tilde, the estimate error terms. And finally, you can see that it's negative semi-definite and it's semi-global because this condition, okay, for this to be negative definite, it requires the control gain to be large enough given the beta 3. Beta 3 is the control gain. So given a fixed beta 3, given a control gain, you need to increase another control gain such that it can involve the initial condition of Z, okay, which is the tracking error. That's for the rise control with multi-layer neural network. So the reason I speed up, right, and I don't think every one of you will use this control approach. I hope this course will help a lot, but I don't expect every one of you to understand or 100% realize this, right? And I just add SC in here. And I ask you to design high gain, high frequency adaptive, right? For the adaptive control, the answer is no, right? Because this structure is not linearly parameterized. So you cannot use adaptive control. You don't need to go through all the design process. I see some of you write down the whole process, all the design equations on the paper. It takes 1 or 2 pages, but the answer is no. You get nothing. So I don't want you to do calculation. Just think before you do it. Relative new topics in nonlinear control. So remember what we have been covered in this semester is we design controllers for dynamics, for continuous dynamics, right? For systems with this continuous dynamics. For example, we design controllers for functions for dynamics like this. Or for linear systems, we design controllers for this kind of systems. Or this is continuous, right? F is a continuous function. U is a continuous function, right? AX, X is constant, B is constant, but this is a continuous function. This is a continuous function. For example, U is minus kx feedback, right? And x is a continuous function as long as the right-hand side of the equation is continuous. Sometimes we put this high-frequency control in the control, but we say this is discontinuous, right? High frequency is discontinuous. Sine function is discontinuous. So in this case, the system is discontinuous. But most of the case is continuous. Okay, we don't quite like these discontinuous systems. But in reality, in our life, many systems can be modeled, or many systems is a combination of continuous and discontinuous systems. For example, when you drive the cars, you switch the gears from 1 to 2. The dynamics is discontinuous. 你换挡的时候 dynamics 其实是不连续的 right? For example, switch the gears. Play basketball, right? You apply a force on the ball, right? And it goes down to the ground with some velocity, right? And you are bouncing back, right? After you hit the ground, you are bouncing back. So in this stage, after the ball released from your hand, the Gamma equation is just dominated by the gravity, right? So it's a continuous dynamics. But until the ball hits the ground will give another force here, so that it can change the velocity V1 to V2. Engineering people model this dynamics. They assume that the force applied from the ground happens instantaneously. It's hard to estimate how long the force from the ground applied on the ball. Okay, so they assume that happen instantaneously. When you model this dynamics, there will be one system F1 in here. Here is F2. So you can see that one is F1, F2. If F1 is not equal to F2, which it is, right? The dynamics is discontinuous. Okay, same as when you drive the car, you switch the gears, the dynamics is. So for this case, we haven't discussed how we can design controllers on switch control systems. But there's a way to design controllers for the systems with continuous and discontinuous dynamics. Okay. So differential equations, we said, given a differential equation, for example, this is a differential equation, right? The x star equal to fx. F is a continuous function. But if you want to model this kind of dynamics, in one system, you switch between t from 0 to t0 to t1 and t1. The dynamics can be modeled by this ODE. And from t1 to t2, you have this dynamics. So can you model, how can you know the solution of x? If you given this differential ODE, we can solve the solution, right? But how about this? We don't know the solution. The solution cannot be obtained using this approach. To model this, we call it differential inclusions. X star belongs to capital F. And capital F is a combination of these two dynamics, which is defined as a convex linear combination of F1 and F2. Capital F is a convex set of F1 and F2. Okay? It's a set, not one differential equation, not one function, it's a convex of two functions. So it's a set. 它不是一个 F, 它是很多 F. And the set of F is this. It's a linear combination of F1 and F2. And the coefficient is alpha, which is between 0 and 1. Every of this function with different alphas. When you see this deep bracket, it's a set. 很抽象. So there's no unique solution. It's a set of solutions. So this is what my advisor told me to do like 5 years ago when I was first year of my PhD. He said, hey, go to study switch control. And I know this, but I don't know that. It took me a long time to explore the area and apply the theory on different applications. And there are many different systems in the world can model by these differential inclusions. Like when we do network control systems, we have multiple robots cooperate together, and they are in which each system require the neighbor informations by communication. But in reality, the communication channel can be unreliable, right? The communication can disconnect and recovers. So because the feedback depends on the neighbor information, so when you have communication disconnections, the feedback will change, and the change is kind of like this. It's discontinuous. So the system switch between different dynamics, so they can be modeled by differential inclusions. And your job is to guarantee that the controller you design has to stabilize the system no matter which alpha it is, because X is belong to a set of F, not an equation. In all these conditions, you need to guarantee the controller can stabilize the system. Okay.